When we think of space, one of the first things that comes to mind is how cold it must be. But how cold is it? Really, what does it mean for something to be cold in the vacuum of space? And how does that affect astronauts, spacecraft, and even the behavior of the universe itself? Let's explore the surprising truth about the temperature of outer space. To start, we need to understand that temperature is a measure of how fast particles are moving. In everyday environments, we can feel hot or cold because particles like air molecules are transferring energy to or from our bodies. But space is nearly a vacuum, meaning it contains very few particles. So the traditional sense of temperature doesn't work the same way in the emptiness of space. Despite this, space does have a temperature. The average temperature of empty space, far from stars and galaxies, is about 2.7 Kelvin. That's just above absolute zero, the lowest possible temperature, equivalent to minus 454.8 degrees Fahrenheit or minus 270.45 degrees Celsius. This temperature comes from the cosmic microwave background radiation, which is a faint afterglow from the Big Bang still lingering in the universe. However, space isn't uniformly cold. The temperature can vary dramatically depending on where you are and whether you're in direct sunlight. For example, on the side of the International Space Station facing the sun, temperatures can reach over 250 degrees Fahrenheit, while the shaded side can plunge to minus 250 degrees. This huge swing is due to the absence of an atmosphere to distribute heat. Astronauts and spacecraft must be carefully designed to handle these extreme fluctuations. Spacesuits contain multiple layers of insulation and reflective material, along with heating and cooling systems to keep astronauts comfortable. Similarly, satellites and probes use thermal control systems to protect their instruments and electronics from overheating or freezing. One fascinating aspect of space's coldness is how long it takes for objects to cool down. Since heat in space can't be lost through convection or conduction, because there's no air, objects in space lose heat through radiation alone. This is a much slower process. That's why, for instance, spacecraft like the James Webb Space Telescope use large sun shields and take weeks to reach their optimal cold operating temperature. Cold temperatures also affect how materials behave. Metals can contract, lubricants can freeze, and electronics can fail without proper temperature regulation. Engineers must test every component under simulated space conditions to ensure reliability in these harsh environments. In deeper parts of space, far from any stars, temperatures drop even lower. In dense molecular clouds where stars are born, temperatures can be as low as 10 Kelvin. And in certain shadowed craters on the Moon and Mercury, the temperature can reach below 30 Kelvin, some of the coldest places in our solar system. Interestingly, scientists have created even colder environments on Earth. Using lasers and magnetic fields, researchers have cooled atoms in laboratories to temperatures just billionths of a degree above absolute zero, colder than anything found naturally in the universe. These ultra-cold experiments help us explore the fundamental laws of physics. Despite the harsh cold of space, life on Earth exists because of our planet's protective atmosphere and the energy we receive from the sun. Our atmosphere traps heat, moderates temperature extremes, and allows water to remain in liquid form, essential for life as we know it. Space's frigid conditions also play a role in preserving the past. Space probes left on the Moon or other celestial bodies remain intact for decades or even centuries because there's no weather, atmosphere, or moisture to cause decay. In the vacuum and cold of space, time moves differently for physical objects. So, how cold is space really? It's about as cold as it gets in the known universe, but with dramatic variations depending on location and exposure to radiation. Understanding these temperatures is essential for space travel, astronomy, and the future of human exploration beyond Earth. If you found this journey into the chill of the cosmos fascinating, don't forget to like, share, and subscribe for more incredible science explained.